together. Okay, so great. So the fission fragment flying in the middle is catalyzed this kind of gas and produce a signal. Okay. So so the potential for this the average energy is very important. That's it. And from this result, okay, this result is a signal caused by the alpha particle, because the uranium can, well, with the alpha decay, can also produce the very small signal, and the fission fragment also. Here, example, use this fragment. We can see the difference is very large. This fragment is cause very strong signal. This is current. This is current much higher, of course, much higher than the alpha particle. So we change to the pulse, the voltage. So the voltage of the fragment is very large. And during the simulation, we also to change or to modify to simulate the pressure in the chamber, the gas, example, the argon gas in that chamber, which was example 1 atmosphere or 3 atmosphere. Okay, so the counting ratio is almost the same, but the height of the pulse can be changed as the pressure increases. So we just according to another product from company, we choose the pressure about 2 atm. So in our detector, we use this pressure. So we also to simulate the distance between the electrode from example from 1.5 millimeter to 3.5 millimeter. And also here we change the thickness of the uranium layer. Change the thickness. So finally, we set the distance and the thickness as these values. Another result of the simulation is percentage for the gas. The uranium layer and the electrode. That's difficult. So with the design, we use this kind of parameters: the size, distance, the material. This kind of the detector. So we start to coating. We start to coat. We choose 2 kind method. One is this one, just something like the water, okay, and this you find the organic phase to coat and get the result or the best parameters during the code. Okay. After that, it is difficult to search for the best parameters during the coding. So after the coding, we have to test. Okay, here's the yellow one, the uranium layer. Actually, maybe the uranium oxide something. So there's no standard to judge it's better or it's worse. So we have to develop some kind of standard to judge how about the adhesion. This one is we just cut the surface, the layer to very small piece and use a tape to strip the layer. If it's very strong or very hard, oops. So and after we straighten the layer, we use the alpha detection system to test the alpha particle from each part. Yeah, that's very easy. So this one, and here, we try to use our detector in the example the fourth generation fission reactor. So with very high temperature, we try to increase the temperature about 500 degrees centigrade or 800 degrees centigrade. We test. That's here some not so good. 800 degrees centigrade. No. Then so we get this detector like here. Here. This room is very not clear. So this is a detector, and here actually here's a neutron source. The neutron source. I don't know how to see the name of the neutron source like here. But beryllium neutron source, right? So and simulate. Or also we simulate this one, and we found that the real counting the counts, and here is simulation almost same, almost same. So this that means here also the measure the test. Okay, the red one is the result of the test, and this is the simulation. I almost think that is another thing is the so-called wide region. Wide region that from very low yield to very strong, very high yield. We have to, especially when the fission reactor is start and working, right? So the yield change the range is not very large, but very huge. Okay. So we use so-called three model electronic system. Sorry. So example here is a so-called fission chamber and the bar supply. Okay, from we measure the power. Oh, here. Yeah. This one. Oh, yeah. So from the chamber, the preamplifier, and here is the power output and the conveyor model, and here is current model. So three model. And here is from here to here is the conveyor model. And the
We still have 3 minutes.
oh, okay. So this is the parts model, conveyor model, and the current model. So we can set for very low counting rate or very large counting rate. Okay. So I will just skip this one. And so here is a conveyor model, and then this is some power shape, amplifier, and in the middle, and the shape. Okay. And the test below. Oh, and we compare the example of the counting rate from 500 hertz to very large one during this model, and almost linear. So the powers model is very simple, right? So very simple. Okay. and the current model. So we use almost four parts set to get the synchronous, like, as so the final output is current. So here finally we get this one, and yeah, the we compared our this model to the paradigm, the Altec 142. Yeah, this one is about 8, so far you get 15,000 yuan, right? 50,000 yuan, but here might be, yeah, 800 yuan. Right? Yeah, it's very cheap, right? Very cheap. Uh, 800 yuan. Oh, yeah, that's a final. Okay, summarize. So first, we integrate with many software actually together, just for design efficient chamber. We can change the parameter in and immediately we give the result. Okay, and we also during the coding process we found some optimize the parameters, yeah, and also the testing method. So far, no testing method to judge the quantity of the coding layer. Right? And also you get the three model, the so-called parse, compare, and the current model for the this one. And yeah, we hope that one can be used in our fusion reactor in the future. Okay, thank you.
Any questions? Yes. Very sound.
Thank you very much for your talk. I have a question. If you said you exploit fast fission and you are using natural uranium in your detector. I am wondering about the applicability to proton boron neutrons because, for example, from the alpha 411 reaction, you have neutrons which have a relatively low energy around 160 keV. So, if I remember correctly, for uranium 238 below 1 MeV, the cross-section for fission is really very low. So
Yes.
I am wondering about the efficiency of your detector for the relatively low energy neutrons from alpha B11 reaction. Is it so efficient?
Yeah, actually, this one was used to the east, DT.
Yeah.
DT reactor, the east in our country, the east. Okay. You see as a nuclear energy very low, almost no reaction, no fusion for the natural uranium. But we hope someday the government will let us use the enrichment uranium. So we just like I said, develop such kind of technology, right?
If you offer rich with uranium for to fusion.
Yes, I want to say because this one is actually is very cheap, very cheap,
Technology is there.
almost nothing. But we import from America. It's about 400,000 Chinese yuan. It's very expensive.
Sorry, a very naive question. In your system, every time you detect a neutron, you destroy one uranium atom. So the sensitivity will decay in time.
你这个碰撞一下，那个油少的话，你sensitivity 对你的敏感度就会降低。
Right. So you see the thickness of the layer. Almost
really decreasing.
or the
你的原油少了嘛，
right,
然后就会你的敏感度降
of
低。
course. Of course.
So what is the
To change the material, I guess.
what is the
What's the lifetime of your detector?
Yeah.
So I never tested in the fission reactor. Yeah. Maybe, yeah, we guess maybe 2 or 3 months in the factory in the Mars. In the fission reactor.
We run out of time, so thank you.
Okay, thank you.
So, the third speaker in the first section will be online. It will be given by, Orisa Cambodia. Orisa.
Good morning, everyone. Am I audible?
Yes, yes.
Good morning from India.
Yes, Orisa, welcome.
Thank you so much.
Okay, so so you will be the third and the last talk in this first section, and please, I think you can start. You have 20 minutes, and I inform you in 3 minutes ahead. So please start.
Definitely. So I'll share my screen.
Okay.
So is it visible?
Yes.
All right. So before I begin, I would like to sincerely thank the ENN group for letting me present online. So we had a big struggle in getting visa approved. Unfortunately, I couldn't get it, and I have to present online. Although I believe that conferences are meant to be, meant to happen offline only, because that is how we connect. And I'm very grateful to Professor Dr. Dieter H. Hoffman sir. I'm really thankful to him for letting me present and to show the work to the people who are really working in proton boron fusion. So the work which I'll be presenting is suppression of parametric instabilities in proton boron fusion plasmas. This work is done in collaboration. So I am Dr. Oriza Kamboj. I am from Symbiosis Center for Research and Innovation, Symbiosis International University. This work is done in collaboration with Dr. Nitikant, who's from University of Allahabad, and Professor Hoffman, who is in Jiang Yangtong University, and in collaboration with ENN group as well. So the first slide is basically I'm going to talk about why proton boron and why now. So basically the reaction in the top of the slide is just telling us that a proton and a boron 11 nucleus will give an alpha particle and 8.68 MeV of energy. So these products are charged. There is no primary neutrons. So there is no tritium cycle, no 14 MeV loading on the first wall. So the fuel is ordinary proton and ordinary boron. So the things that have changed recently is that the cross section came back to 12 to 50% higher, about 30 keV. And the laser experiments report about 10 to 11 alpha particles per shot. So this is a serious commercial investment which companies and people have started to look on. And if we look at the bottom box here, it sets up the whole talk. the price of admission in the ion temperature is 150 to 300 kilo electron volt, and a Bremsstrahlung budget that forces tau below one half. So both for outside deuterium and tritium experience, this is we have this kind of experience. So the question, I am being very, I shouldn't say nobody, but I should say the question which less people have quantified. This is about the parametric instabilities, which are a serious concern in inertial confinement fusion. So if we look at stimulated brilliance scattering on the left, the pump decays into scattered light and ion acoustic wave. So what happens here is that you lose the energy and you get asymmetry in this case. Whereas in stimulated Raman scattering, the pump decays into scattered light and an electron plasma wave. That makes it hot, and hot electrons preheat the fuel, which is a major concern in ICF. And in TDP, the pump decays into plasma wave where the quarter critical surface, near the quarter critical surface. So we get very low threshold and more preheat. So now this is what the intuition or the concept which it was built upon, this work was built at a few kilo electron volt in one ion species. So with electrons which are hotter than the ions. So proton boron inverts all the three at once. This concept is going to invert all the three at once. And proton and the electron temperature is 10 to 30 times higher. 10 to 30 times higher. So there are 4 species and the ordering runs backwards. So we cannot extrapolate. So all the calculations which are done has to be redone kinetically, and that is what we did in this work. So if I talk about my plasma model, so on the left hand side here, I'll move quickly. The model is basically collisionless because the collision rate is far below the wave frequency. 4 species at a common ion temperature, we have considered a proton boron ratio of 9, giving an effective charge of about 2.4. And a micron driver laser that we have considered. On the right hand side is basically the machinery, the analytical derivation. So the top box is talking about kinetic dielectric function. The important part is the function Z, the Fried-Conte function. It gives us the kinetic damping rather than the fluid estimate. And that is the difference that decides the answer. In the second box, we are talking about the growth rate in uniform plasma. And in the third box, we talk about the Rosenblatt convective gain in the density gradient. And we get a daughter exponent damping as well. So in the blue box, which is the final version here, amplification matters once again because the gain reaches about 15. So this number has to be noted so that the next slides can be understood, which are the result slides. So if we talk about stimulated brilliance scattering, the ion acoustic wave here is critically damped. So backscatter fixes the daughter wave at twice the pump wave number. So at 50 kilo electron volts and 1/10 of the critical density, that gives lambda debye of 1.88. So that is what we are getting here. And for ion acoustic wave, this is fatal. It's going to go down really. The phase velocity sits inside the bulk of the which I believe that because it is sitting inside the bulk of the proton, the distribution rather than at the tail. So what is happening is the proton absorbs the wave very efficiently. Now, if you look at the figure, the horizontal axis is k lambda debye, and the vertical axis is the damping ratio. So the solid red curve on the plot, the solid red curve which we can see here, is our case of tau of 0.25. And the dark dashed line is the same plasma at tau of 1. So these are overdamped and underdamped for comparison. So now if we follow the vertical dashed line here, vertical dashed line, the pink line here, at 1.88 at this particular point, that marks the brilliant scattering wave vector. Where the line meets the red curve, the damping ratio is about 0.98, which is around here. If I talk about the second result, our stimulated brilliant scattering, the gain sits at 20 orders below the threshold. So on the part A, the left hand side, the intensity cross section is upwards, and the solid red line is rising across the plot, and which is basically the growth rate. The flat red dashed line above is the ion acoustic damping rate. So if you notice the dashed line, it always stays above the solid line. So damping is winning everywhere. And if we look at the part B of the result on the right side, there are three red curves, basically three density scale lengths, and they lie on top of each other. So we are able to distinguish a little on the higher side, but here it's almost on top of each other. And the black dashed horizontal line is the threshold. Now, at our reference intensity, the gain is around 10 to the minus 22, and that is 22 orders of the magnitude below the threshold. And one honest point, since you can see here, is that the curves do not cross the threshold at far right. Now, those intensity near to the 10 to the power of 18. Now, at those intensities, the pulse ends long before the convective gain. And if I look at the backscattering, that stimulated Raman scattering, which I was really interested in. So if we look here, that this is the central result of the talk, which the entire paper is based upon. So for the backscatterer, the electron plasma wave has to carry twice the pump wave number. If we put into the Bohm-Gross relation, you will get an expression which is on the top, which is explained here. The thermal correction grows in the direct proportion to the electron temperature from this. So if now we are applying only the requirement that matters. The plasma wave frequency must stay below the pump frequency. We are applying only that. So otherwise, no daughter wave can conserve the energy and the process cannot happen at all. So if I rearrange the underdense limit and everything collapses into a single gold line box here. So what we get is that the electron temperature must be below MEC square upon 12. That is around 42.6 kilo electron. So if I'm being precise, this means that this is not gain that happens to be small. This is not a threshold you can overcome with more intensity, unlike what we were thinking in ICF. So there is no resonance available at all. So density will not help, intensity will not help, composition will not help. Now if we look at the panel figure on the A side, temperature is upwards here, and a density cross section, and the horizontal dashed line is our limit. This is our limit, that 42.6 keV. And everything in the pale red region above it is kinematically forbidden. So this is the forbidden area. And the green region at the bottom below solid curve is where the matching is still possible. So proton boron runs at 50 keV and above. So that is above the dashed line, which is inside the forbidden region. Now, if we look at the SRS forward scattering, the stimulated Raman scattering in forward way. So we say that here the plasma wave is long wavelength, so the matching is comparatively easier. So it stays allowed up to 0.15 of critical density of 50 kilo electron volt. So in the part A, what we can see, there is a red dashed line. This is the growth rate. And in the panel B, the red dashed line curve is the gain. And the black dashed horizontal line is again 15, right? So this is negligible at the reference intensity. Threshold is reached only above 10 to the 17. So now the third instability that we went for is TDP. And here I want to change my sentence a little because it will be overall easy to oversell the message of this talk. In one of the basic gold papers of Liu sir, the proportion, it is proportional to the electron temperature and inversely proportional to the density scale of length, which I have written here. So at 50 kilo electron volt and 500 microns, it gives 5 times the 10 to the 12 watt per square centimeters. So this is against the deuterium tritium at 3 kilo electron volt, and this is an order of magnitude which is way higher. So the high temperature helps us here too, which I believe, that which I have been showing in the figure, that the 4 color curve lines here, so they are 4 scale lengths. The blue one on top is 100 micron. The red one on the at the bottom is 1000 micron. So the pink band which we are seeing here is our temperature range which we have plotted. The gray dotted horizontal line near the top is 10 to the power of 15 centimeters. So if we notice this, all 4 curves lie below this dotted line, right across the pink band. Right across the pink band. So a drive at 10 to the 15 sits above 2 plasmon threshold everywhere in the operating range. So here, that is what we have stated, and I will say plainly that the expression in the threshold for the absolute instability from a homogeneous estimate is given. In a long scale length plasma, convective amplification can occur below the nanosecond driver, will routinely sit above 10 to the 12. So I'm not going to tell you that the 2 plasmon decay is suppressed. This is not a claim, and it is not, as we can see, it is raised and it is weakened. And whether it is sufficient depends upon the intensity. So we have a lot of work still to do. We have a lot of exploration still to do. So I believe this is an area that can be explored. So if we look at TDP's angular spectrum, the second half of the TDP story, which basically is that the daughter wave number goes over the cosine of the angle. So it should climb steeply because we have a cosine angle here. So it should climb steeply as the pair opens out. So in this plot on the left, angle in the degrees across, K is the debye upward, and the bright red curve is 50 kilo electron volt. The dark red curve is 100 kilo electron volts. So if I follow the bright red, it reaches the value only about 74, and at this point, and the dark gets about 67. So the wide angle pairs are much more heavily damped. So the angle is high, the damping is more. So this is the ultimate result that we have obtained. And if I look at the stability map, the unified stability map, all the 3 panels, the density is across and the temperature ratio tau is upward. Now blue color here means low gain, the red means high gain, and the play blue band along with the bottom of each panel below tau of 1/2 is where the proton boron actually operates. The proton boron actually operates. So the middle panel here is Raman scattering. And here I want to point out something myself rather than, you observing. I will straight away point out that along the very bottom edge here, the gain rises. Now, this is not a numerical noise. I believe that at ion temperature of 200 keV and tau of about 0.21, this is exactly where the electron temperature should fall back to 42.6 keV. That is why we are observing. And on the right panel is the 2-plasmon decay. It is blue until you reach the strip near quartile critical density. And then the red. So precisely there is the surface which you cannot avoid. So just to shorten this up, what actually we did in this work is, which is a very fair question, and how much of this is really about proton boron and how much it is about simply about running about hot plasma. So this is the comparison table we run, and the honest answer is temperature. So if we look at the lambda Debye ratio, lambda Debye rho, in the both columns, the tritium plasma is strongly damped, and the Raman prohibition depends only on the matching condition. What genuine specific proton boron is on the right slide, which is here, that the inverted tau which deepens the ion damping because the sound speed drops into the proton bulk. Now, as the multiple ion species, which changes the coupling ratio. So I would rather plainly say that we have a big discussion here to talk that the temperature does most of the work and the proton boron's specifics refine it. So my conclusions would be that, just to summarize, brilliant scattering, the ion acoustic wave is critically damped and the gain is 20 orders of the magnitude threshold. So it is basically negligible, it is gone. Whereas if we talk about Raman scattering, backscatterer is kinematically prohibited above 42.6 kiloelectron volts, which covers the operating window. And forward scattering is allowed, but it carries no useful gain. And 2-plasmon decay, the threshold is raised by the order of the magnitude, which widens the angle pairs, which is damped, but it is not suppressed. The quarter-critical surface still deserves a proper inhomogeneous treatment, which can be further analyzed, and as I keep saying, it can be further done. So this is the open item for the work. So within the stated assumptions, whatever we have assumed, parametric instabilities are still, I believe, not a principal obstacle, but we have a lot to explore. So thank you very much for giving me the opportunity to speak. And this is my university. We are sitting on a hilltop. It is very beautiful. And we are open to any kind of theoretical, I am in theoretical and computational work in the laser plasma interaction. So whoever is interested, I am very much open in discussion or any further questions. Thank you very much. Thank you.
Excellent. Thank you, Marisa. So now we have questions.
Thank you very much for your talk. I think it is important to study this kind of topics. Indeed, I agree with your conclusion that the suppression of the parametric instability is driven by the high temperature, because in reality, a proton-boron fusion plasma is not very different from the ablation plasma, which is produced from a plastic ablator, because carbon is quite similar to boron. Now, the question now is, you are speaking about temperature of the order of 25 to 100 keV, which are relevant for proton-boron fusion, But in an inertial confinement fusion approach, this will not be the temperature of the corona plasma. This will be the temperature of the core. The corona
Right.
plasma will always have temperature of about a few kV driven by the laser interaction. So I think that in this case, the parametric stabilities will always be there and will always be strong.
Okay, okay. So, as I told you, in the last line, I've mentioned that based on these parameters, the conclusions were given out. But I think we can explore that part. I think we can change the parameters and observe and compare how ultimately it is getting affected.
So we have another question, please.
Thank you for your talk. Your results are interesting, but did you analyze the possibility to use proton-boron fusion and inertial confinement for power production in general? The main obstacles for the use of proton-boron explosion for power production is the following. This reaction is very slow. The temperature necessary for ignition is not a problem. The problem is that reaction is slow. Therefore, at the attainable densities, the block of compressed fuel should be so large that if we want to get the realistic air, that the total yield will be unacceptable. Something I'm sorry, I speak about this here for the third time, but you did not attend the yesterday activity of the conference. So it seems currently that use of inertial confinement and proton-boron reaction for power production is impossible in general because the density of the order of 100 grams per cubic centimeter and target gains interesting for power production correspond to an acceptable total yield of macro explosion, which cannot be called micro explosion in such situation. Did you analyze such problems?
Hello?
Yes, can you hear us?
So, hello?
Can you hear us?
Should I repeat my question?
Well, please repeat, sir. Please repeat.
The problem is the following.
I'm not able to understand. I'm not able to understand your question, sir.
Do you understand my question?
I'm not able to understand your question, sir. The voice is echoing, I believe.
Can you please repeat? Maybe you stand here.
So the main problem with the use of inertial confinement fusion
Inertial confinement fusion?
Inertial confinement fusion, if used to ignite proton-boron reaction, has the following problem. The reaction is slow. And therefore, when you compress the fuel to the realistic density of a few hundred grams per cubic centimeter, and you want to receive good gain, especially, for example, of about 100, as usually discussed for DT fusion.
The voice is echoing. I'm not able to hear. Sir, if possible, I think this is a big discussion. If possible, I'll write down my email ID. We can discuss this over.
Well, I will write later, but the same, the total yields.
Hello?
Is it better now?
Can you
So
hear?
Yes, the voice is breaking, sir.
Can you hear us now?
Sir, yes, I can hear you now.
Did you analyze? Did you analyze the macro explosion yield corresponding to the realistic density of compressed fuel and interesting target bearing?
I think, sir, this is
Okay,
a good
so-
point of
so I-
discussion, but the
I
voice
suggest-
is breaking. Can I just write down my email ID? And this we can connect over email and we can
Yeah, yeah.
discuss this. So I will write
Thank
that
you,
down.
Ariza. So I suggest maybe you discuss afterward by email or something. Okay. Thank you, Ariza. There's some delay, seems.
Okay, thank you. Thank you.
Okay, thank
Yeah,
you.
I'll give my email ID and we can definitely discuss over it, sir.
Okay, okay. So thank you, everybody. So this is the end of this first section. So let's thank all three speakers again. So now we have break.
I guess it's operating around but you can be quiet. As low as 0.3 or 0.5, depends on the operational mode that's and
你自己看一眼，我们刚才调了一下，
啊，行，应该他过就行了。
我们刚才调了一下，效果
我们早上才发的，可以。
可以是吧？
高能的基础就是primarily process，
这个另一个是谁？关香台吧？
对。
他上传了吗？
没有。
And this is a very electron. Going through the rather tenuous does not always allow the target is very dense. But these electrons for elementary and when we have air still on the wall. And that is the primary source of that rising power. Think targets. But these are actually the actually status that was so it's very so I will be about what the active right. The energetic electron and we have seen our highly efficient production of the energetic very
对，我把声音调小，要不然太吵了。 真的出去
I will give you.
你可以睡觉了。
So
Okay, shall we start now? Okay. Please come back to your seat. It's time for the last session, last academic session. Sorry. 哎，你看他唱的听电脑是期待。Let's welcome the last session. There are two reports in this session. The first is by Professor Wang Lei from Chongqing University. He will present the theoretical simulation and experimental verification of telecom wave dischargeable boundary density control in a colloidal fusion plasma. So you have 20 minutes, and I will notice before 3 minutes. Okay. before presenting.
Sure. Thank you. Thank you very much for introduction, and thank you very much for allowing me to give my talk in this conference. And sorry to interrupt your coffee break. I hope my talk will be interesting and worthy.
We're late.
Thank you. Sure. So my talk actually, it is a novel exploration of a new direction of using Halligan discharge to modulate the edge density for toroidal fusion machine. So some of you may doubt my judgment, saying that this is the first exploration because Halligan plasma has been already used in many aspects in fusion plasma, like that Halligan wave heating and current drive, which is already happening on the D3D and the K-star tokamaks, and also Halligan waves and discharge has been used for the first raw material testing, like the MAGPIE machine at the Australian National University, where I worked on for my PhD, and the MPAX in the Oak Ridge, right? So these two machines are famous for the first raw testing using Halligan plasma. Also, Halligan plasma was used as the wall conditioning, which has been employed on the East tokamak in Hefei. So, and moreover, Halligan plasma was used as the ionization stage, like for the stellarator in Canberra, which now the stellarator has moved to China. So Halligan wave hand discharge is also can be used for the ionized to produce the plasma inside the fusion device. So basically, Halligan discharge has been used already in many aspects of fusion. For fusion, but my talk today is about a new direction to use the Halligan discharge to modulate the edge density of the fusion, to improve the coupling efficiency of the RCH and other heating method. So first, I will introduce the background and the significance, because as I read the menu of this conference, not many talks are about the heating, and about Halligan plasma, this is the only talk. So I'll give you some introduction. So basically, why we need to modulate the edge density, because as you know, the RCH is still the main method for heating, because it has a high power capacity, cost effectiveness, and low impurity generation, and other benefits. So, but you know, at near the edge here, the edge density here, normally like 10 to 16 per cubic meters, that this low density here limit the wave propagation of the RCH heating. And we need to increase this density near the antenna here, in front of the antenna. Currently, there are two methods. One is to move the antenna closer to the core plasma. But this causes another problem, like this severe thermal load and impurity contamination. Another method is like this puffing, gas puffing, near here. This can also increase the edge density. But you know, for this gas puffing, it's difficult to control the flow, and it causes another like radiation losses. So basically, we need a new method to solve this problem, to increase the density near the edge here. So this talk is trying to explore a new method called Halligan discharge. So I need to go back to what is Halligan wave. You may be familiar with this figure. If you plot the cold plasma dielectric tensor directly, you get this dispersion relation. And in this branch here, it is called Whistler. So Whistler is more familiar to you, I guess. And with on this Whistler branch, if we have the frequency between this ion cycle frequency and the electron cycle frequency, so this area is called Halligan. This is a Halligan wave. So if we Halligan wave can not only propagate inside plasma, but it can also to generate plasma. So this figure shows the typical Halligan discharge facility. This is like a linear machine. Basically, we just need some antenna wrapping around a cross tube and confined by some external magnetic field. Then we can have the plasma, a Halligan discharge. So this is for the antenna wrapping around the cross tube. And also we can have this planar antenna to plate near the one end of the cross tube to excite the plasma actually. So these two methods. So this figure shows the advantages of Halligan discharge. So compared to the conventional CCP and RCP, hydrogen discharge can produce plasma with density much higher than them. You can see here, 10 to 13 per cubic centimeters. Actually, it is now we already achieved 10 to 14. So it is much higher. Moreover, hydrogen discharge, to my best knowledge, is the only discharge that can achieve full here. So previously, people using this like these two methods to generate hydrogen discharge, but for our project, we need to modulate the edge density here. So the scheme is totally different. So we put the antenna here outside the chamber. This scheme has several advantages. First, it is outside the vacuum chamber, so we do not need to set up inside. We do not change the environment inside. So and it is easy for us to change the antenna, right? Because it's outside, so it's easy. And different from previous scheme that we use the planar antenna here, and the antenna you can see it faces the magnetic field line. It is vertical. So you may doubt that it's similar, but it's different from previous here. This is also planar antenna, but for this antenna, the magnetic field is this antenna put this way to excite plasma in this way. But here we put an antenna from the side window, so it can excite plasma in this direction. So 90-degree different. So that's why I call this is a totally new scheme of hydrogen discharge. So after this background introduction, I will go more details, go to about this project. Yeah, so this talk is not organized as a traditional academic talk, but in terms of project summarization. So for this slide, lots of text, sorry. So to show the status of this this performance. So first, we already studied the helical wave propagation mechanisms and power deposition, dynamics, structure, optimization, antenna, and even this dielectric window, and also to validate this side window discharge configuration on 12 devices. So basically, we already achieved this single stage helical discharge to modulate the edge density, and also ECR. So two stages, ECR and helical plasma. This two stage is also verified. Next, we are going to move to this verify whether the modulated edge density can improve the coupling efficiency of the SH. This work will be done here in ENN. We are in discussion now for experimental proposal to do this experiment on the channel 50U here. So during the last 1.5 years, that we already finished the theoretical and numerical simulations. So we built this three-dimensional full device electromagnetic model to calculate the wave propagation and power coupling. And also we simulate how the wave propagate from the edge into the core region with a very steep edge density gradient. And then moreover, we calculate the and spatial evolutions of the helical discharge with a very detailed evolution of the density and the temperature. So I will show more details later. Here it is just a summary of the progress. Therefore, the experiment, as I mentioned, that we have done lots of optimizations, including the antenna geometry, the position, and the frequency, pressure, magnetic field geometry, and strength, lots of parameters. Then we already achieved this edge density modulation. The peaking density is like here, this value. It is 2.2 times the 10 to 18. This is a helical discharge level. And we already also combined this ECR with helical discharge and achieved the synergistic heating here. So next we are going to move to the SH stage. So these are some publications about this project. Now it is just midterm, not finished yet. We will still have another 1 year to go. So we already have 6 publications here, and so this year we have 5. So most of them are simulations work. So next we are going to move to experiments, and actually the experiments work is in written. This is the progress here. We already completed this simulation and theoretical analysis, and also completed this first and second stage experiment. And this work is under preparation for a paper. And then this is the next stage. We're going to move to validate this idea can be used for the RCH and in progress. So this project will be finished next year. So next I will go to the detailed summary of each work. So first, this is the three-dimensional multiphysics modeling. I named it the themis here because it uses a hot dielectric tensor and can calculate the wave for propagation and power coupling. So this is the geometry of the toroidal device. So this is where the helical wave attend here. So we just excite the helical discharge from this small window here, and it can generate plasma through the whole toroidal direction. And but this window is complicated. You know, this I will mention later because this thickness of this chamber is very thick. It's 10 centimeters. And sorry, so it causes a waveguide here. So previously we put a antenna outside this convex window. We find that the wave field is localized near this waveguide, cannot propagate inside. So later on, we move this side of this cross window that inside into to make it a concave window. So 10 centimeters, but this is a key. So now the plasma is closer, much closer to the antenna, and improves the coupling efficiency significantly. So we did a lot of experiments and simulations to test the different antenna geometries. Like here, we tested 4 antenna designs, including this is a rectangular, this is a spiral, and this is cone, and this is the wrist track antenna geometries, and compare this is the real dependence of their parallel wave number with this radius to compare. And yeah, because of limit time that I'm not going to quite detail about the optimization, so I just show you the result. So after lots of optimizations, we finally achieved this optimized discharge using this recessed window. So now we have the plasma closer to the antenna, and then we use this retraced antenna here. And this shows this figure shows the planar geometry. This is show the toroidal geometry. You can see the wave propagation and power coupling. So basically, we achieve the 65% observation efficiency, which is an order of magnitude higher than the conventional, short circuit. So we also compare the open circuit and the short circuit. So open circuit is much better. So the second work is that we to study the wave propagation from the side of this low density region into the core region. So this figure is a simplified density profile and a temperature file with reference to the east tokamak. So near the core, we assume it is high density but uniform, but we focus on the edge density, which has edge gradient, both density and temperature. And then we study the wave propagation and the power coupling of the antenna from the side into the core. So this figure shows the dependence of the power coupling with frequency. So basically, if we increase the frequency further, here we just tried this range. So high frequency means a higher power absorption, but it is not single increase. But we need to choose optimize frequency because higher frequency also moves the power absorption near edge, not inside. So at the moment, based on these simulations, we already fabricated the power supply with 970 megahertz. That is the optimized frequency. So moreover, we tried the different density gradient. Like here, this is the decay gradient, means the gradient speed steepness. Yes, so with the gradient increased further, we can see this is the propagation. This is the wave propagation inside here. It changes. I mean, if basically that if the density gradient is so steep that wave field will be reflected, not inside. Here we can go inside, but here it's just reflected and becomes an actual standing wave. So that's why we need like here we need to to take care of the gradient. We also compare the different antenna lengths here from like 10 centimeters to 40 centimeters. So, and we find that this 20 centimeters, it is the optimized length. So this length, because it determines the actual wave number of the wave, so it is important for wave coupling. Understanding well the ionization stage of the Helican discharge, we built this metaphysics work to compute how the discharge ignite and how it becomes stable. So these two figures show the density evolution and the temperature evolution. So this is the first result showing that when the discharge, like here, the density, it increased like here, near 10 to -4 centimeters a second, this stage, and it becomes stable at like 0.01 second. To this is the density. For the temperature, it is much faster. You can see here it is like -4, but here for the temperature it becomes much faster. So basically, the heating process happens much quicker than the ionization. So this shows this is a single like increase, but here this temperature profile shows a non-linear process. So basically, there's a competition between the ionization and heating processes. So, and you can see this figure. For ionization, the density increases from edge into the core, but the temperature, it increases not from the edge, but like from the core. Also, this is the power coupling of in different time scales. At the beginning, that most power is localized near the antenna. Once the ionization happened and we have enough plasma column through the antenna, then the power is coupled downstream and upstream as well. But more overall, that this power coupling is localized near the edge. So this is also an interesting story for Helican discharge. Although the power is localized near the edge, but the density profile is mostly peaked on nexus. So this is an interesting story. I mean, Helican plasma has been studied for like 60 years. So lots of interesting physics still remain unsolved. By the way, actually, I'm writing a book now, which will be finished during this summer vacation. I already finished 150 pages. And this will be the first book of Helican plasma in Chinese. In English, there's already textbook from Shinahara in Japan. So this will be the first Chinese book. So lots of interesting physics about Helican plasma. Oh, sorry. Okay, sorry, I need to move fast. Yeah, for moreover that we studied because lots of physics here. This work is not quite related to hydrogen unboring experiment, but maybe related to your polarization project. Because here we tried so low field to see the low field case. The Helican discharge that shifts from standing region to standing and traveling wave region and to this traveling wave region. You can see how it translated. It's interesting so this low field is a low field peak Helican discharge cannot be explained by traditional like Helican TG mode conversion. We need another theory here. So yeah, so basically also if we increase the magnetic field, so you can see the spectrum becomes narrower and to move to the low wave number. So moreover, I also study the instability caused by the energetic electrons in Helican. Actually, this is the first paper to study the BOT instability in Helican discharge. BOT instability has been already studied well in fusion community, but not in Helican discharge. Moreover, we show that there's a linkage between the micro instability and macro rotation. That's also a first discovery. So moreover, we did lots of work to build this nonlinear region map to show where the instability occurs. So each point here, it is a running case. So lots of work here. We need lots of work. So this figure shows typically 3 different scenarios of the wave mode here. So this is the experiment, as I mentioned, that we tried lots of antenna geometries here. And then first we use this air discharge. This is also outside. This is a convex window and put it here. So for this convex window, we already have this discharge here. So and then we turn on. This is does not have the toroidal magnetic field. If we turn on the toroidal magnetic field, you can see the plasma diffuse toroidally. This is for the air and for the low power here. So just 1 kilowatt. Next, we are using, I'm not sure we have a figure. Yeah. Next, we are also using the argon, and this figure improved significantly. So we have a very clear the belt like surrounding the whole toroidal geometry and near the edge. So we achieved that the edge density modulation using Halligan discharge. So for this figure shows the temperature, measure the temperature here, and also shows the density here. So it is more than 10 to 18 per cubic meters. So this means we are successful here. So this is show the different readers compare the different pressure. So in terms of pressure, it is not a monotonic variation. So we need the best pressure here. We need to match. And this figure shows that if we turn on the ECR, because the Halimark in Shenzhen University was initially initiated by the ECR. So we turn on the ECR to produce the toroidal plasma already. Then we turn on the second stage Halligan discharge. We can already modulate, increase the edge density significantly again. So two-stage also works. So that's what I'm trying to say. So future work, and basically we need to further to to improve the model and to improve this impedance matching network, and to conduct the RCH coupling experiment. Hopefully here. Yeah, sorry, the time is limited. So the existing challenge and proposed adjustments, basically it is the matching. Matching is the biggest challenge because the plasma, especially the ionization stage happens so quickly. So at the moment, we just by hand. Next, we are trying to introduce this optimization to make it dynamic and automatic control. Yeah. Yeah, this is my university. It is not so well known, but it is. Let me mention that it is also 985 in China. We care about where it is 985. It is a 985, and my school's electro. Yeah, sorry, I'm to mention here. The electric engineering in my school is ranked 7 of the 7th of the. Here you mentioned 5, right? Yes, even higher. So this is my group. At the moment, I have more than 20 students, graduate students, so we can do lots of work. Okay, so thank you for your attention. Welcome to visit my university. Thank you.
Time limited, we will have one very fast question.
My question will be super fast. So since I'm a newcomer to Helicon Plasma, I'm curious whether the microinstability you mentioned is turbulence
Which
or
one?
something different.
Sorry?
So you mentioned microinstability in the middle.
Yes.
Is it turbulence?
Not turbulence.
Okay.
It's just instability, just driven by energetic electrons.
Okay.
Yeah, in terms of wave field. Yeah.
So I'm just curious whether you also have turbulence in your plasma.
It is. There's lots of turbulence. Actually, for this project, there's a colleague that in Shenzhen University. Here I use this Halligan discharge to modulate the density. He is studying whether this edge discharge will change the turbulence. Right. So lots of turbulence and transport. Yeah, happen here.
Okay, thank you.
Thank you.
Okay, thanks to the last talk by Chen Shi from Nanjing University. The title is assessing the therapeutic effectiveness of proton-boron capture therapy for brain cancer, a Monte Carlo simulation study.
Hello everyone, I'm Chen Yinshi from Nanjing University. Today I will represent our work titled Assessing the Therapeutic Effectiveness of Proton-Boron Capture Therapy for Brain Cancer, a Monte Carlo simulation studies. Here is the outline. 5 parts. First, the background and methods. Second, physical dose evaluation. Third, nanodosimetry analysis. Fourth, biological modeling. Finally, conclusions and future work. Let's begin with the background and methods. Proton therapy is good at delivering dose to tumors, but its biological effect is limited. PBCT was proposed to solve this problem. Protons hit boron-11 and produce alpha particles. Alpha particles are high LET and short range. They can kill tumor cells more effectively. However, the literature is divided. Some report strong enhancement, but others find no benefit. So we decided to test the hypothesis using multi-scale Monte Carlo simulations. To resolve this controversy, we built a multi-scale simulations framework. At the macro scale, we use Topaz to simulate 3 geometric models. At the micro scale, we use Topaz Embryo for DNA and cell array models. At the nanoscale, we calculated ionization cluster size distribution. Finally, we bridge physics to biology using the LNDM to derive self-survival curves. Now let's move to physical dose evaluation. We built 3 macroscopic models. First, the pure boron ideal model, 1 millimeters cube of pure boron-11 with protons from 0.675 to 10 MeV. Second, a water phantom with a boron target, following Zoom and Ganges settings. Third, the Snyder head model with scalp, brain, and skin. We place the 3 centimeters tumors at 2 to 5 centimeters depths and use 94 MeV protons. This figure shows the pure boron ideal model's results at 675 keV. Resonance peak. The dose, flux, and energy deposition of alpha particles have always remained at extremely low levels. The dose of alpha particles is 10 to the power of -9, and the total dose of particles is 10 to the power of -5. The alpha dose is about 3 orders lower than the total dose. This is the favorable conditions imaginable. Pure boron, no other materials. If alpha dose is negligible here, even here, it will be worse in real tissues. And this page will show the boron doped water phantoms results. At the left figure, we can see the protons results. The black line is the water, and the red line is natural boron, and the blue line is the pure boron-11. With pure boron-11 and natural boron, we can see 2 things. The black peak shift forwards by about 3.4 millimeters, and the proton energy deposition rise by nearly 70%, consistent with Ganges' report. However, but here's the catch. The proton dose drops by 18% because the mass is energy per unit mass, and the boron target is much denser. So the mass increase more by the energy. At the right figures, we can see the alpha components. Alpha dose, influence, and energy depositions all go up in relative terms, but it is relative to extremely small baseline. In absolute terms, the increase is not tiny, and the decisive result is that the total dose drops by about 18.2%, which is identical to the pure drops with a 0.2% difference. This proves that protons dominate total dose. The alpha enhancement is swamped. The table is the material density and elemental composition of the Snyder head per phantom. This figure shows the Snyder hat model's results. We varied boron from 0 to 100 ppm, covering the clinical range. We can see no change in any quantity. At the clinical boron level, the alpha contributions is undetectable. Across 3 macroscopic models, we can see the proton dose is far exceeds alpha dose. Our simulations do not support the physical dose enhancement from PBCT. Now let's enter the key parts nanodosimetry analysis. Why do we need nanodosimetry? Traditional methods use macroscopic dose or average LET. But these approaches average over millions of DNA targets. And over millions targets. It average DNA targets and they will miss the critical detail. Radiation quality is determined by how the energy is deposited in the nanometer scale, nanometer size scale at the scale of DNA. And alpha particles and the proton can deposit the same average dose, but they produce different ionization patterns at the DNA level. So we built DNA chromatin fibers models with 1,800 nanovolutes, each simulating 10 base pair DNA segments. We also built 3 by 3 by 3 cell array models imported by phase-based source from Snyder hat tumor. We consider homogeneous and heterogeneous boron distributions. These figures shows the critical nanodosimetry results, ionization cluster size distributions. Ionization cluster is the number of ionizations built by one primary particle and within a DNA size target volume. It is different from average LET. LET average energy loss over distance and the distance. We can see in this figure the alpha particles is the distributions is extend from V equal 25 large clusters, and for proton particles the distribution is V equal 10. In the mixed PVCT field, the distributions is nearly identical to the pure borons. So we can see the proton distribution completely masks the alpha signature. And the red nanodosimetry proves that alpha contribution is diluted. And this figure shows 3 nanodosimetry parameters. Nanodosimetry parameters is derived from ionization cluster size distributions. N1C1 is the average cluster size, and F2C1 is the probability of ionizations with 2 or more ionizations. It matters because multiple ionizations in close proximity are harder to repair. N1C2 is the average cluster size conditions on 2 or more ionizations. It tells us how severe the damage is when the damage occurs. We test boron up to 1,000 ppm. and consider the homogeneous and heterogeneous, we can see the results is flat. Boron concentration and distribution have no influence on radiation quality. Now let's move to biological modeling with LNDM. LNDM links ICSD to LQ parameters alpha and beta. Alpha means single hit DSB, lethality, and beta means multi-hit SSB, indirect lethality. LNDM does not rely on macroscope dose or average LET. It uses the actual stochastic ionization events at the DNA level. And survival rate is derived via damage probability calculations, linking nanoscale ionization cluster size directly to macroscopic cell survival curves. LNDM predicts alpha, beta, and cell survival are also boron independent. Now is the conclusion and future work. In conclusions, alpha contribution completely dominated by protons at both macro and nanoscales. Boron concentrations and distribution have zero effect on nanodosimetry parameters. Clinical benefit of PVCT is not supported by our data. In our future work, next we will fit LNDM parameters. With V79 and HSG cell data, we will validate predicted survival curves against experiments, and we will calculate RBE relative to cesium 1037 gamma rays. And we will compare with classical LQ, MLQ, and MKM models. This work was supported by the proton-boron fusion research funding. Thank you for your attention.
Thank you very much for presenting very interesting results, but I have a question. Did you study the possibility of a significant biological effect of boron, which could not be related to enhancement of the dose? I mean the following. I completely agree with you that increase in total dose or somewhere near the point of proton-boron interaction, nanoscopic dose is very small. But there are some data which allows us to assume that some other effects could be important. I mean the following. It was shown experimentally that the effect of gold and some other nanoparticles on efficiency of proton and gamma ray therapy can be very strong. And to the best of my knowledge, this cannot be explained as effect related to local dose enhancement. The situation is simple when gold nanoparticles are used in combination with X-rays. In such situation, increase in dose is absolutely simple and evident. But in principle, in some situations, some other effects could be possible. So I think this should be studied, and I would advise you to read the literature on the use of gold and not only gold. Maybe even as for such examples, the materials is not highly important. It is important, but not very much. So some effects not related to those enhancement could be important. And I repeat that I would like to advise you to read the literature on the use of nanoparticles in proton and gamma ray therapy. For example, I discussed the possibility of suppression of DNA repair by electric fields, but there are several other ideas, and maybe the experiments on animals are necessary to the best of my knowledge, manifestation of some effects can be observed only in the experiments with animals. Experiments with cells are very important and interesting, but sometimes they are not sufficient.
Okay, thank you. I will read this reference.
So in a way, my question is related to the question before. It's not a surprise that you measure that the alpha particle contribution to dose is small. You know, in laser-driven proton-boron fusion experiment, which in a way are similar to your experiment because we send the proton beam into boron, we see that the ratio of protons to alpha particles is maybe 10 to the 4. So there are not enough alpha particles to produce a change in the dose. But in reality, I think that the final answer to your question should come from experiment, not from simulation, because maybe there is something which is not included in the simulation.
We will compare the cell data with the experiments. Thank you for your suggestion.
I just have a comment rather than a question. I just want to compliment you on, a very forthright presentation of essentially, negative result relative to a proposed method. Because, it's very important to produce these negative results to prevent wasted effort. And I think that the fact that you're pointing out that even the biological effect is orders of magnitude less than the proton beam itself. I think it's very significant work. So I just want to compliment you on it.
Thank you. Thank you.
For the comment? Well, I just have one question about the mechanism. In one page, you show the beam actually has, shall we say, abrupt interactions on its path with some maybe atom or nucleus, which diverted the track. Could you show that? I just want to understand the physical, the mechanisms that, no, the one with the red dots. The one with the red dots. This one. What causes those branches? What did the ion hit? What is the mechanism?
What's
这是什么？这是什么机制？它碰到什么原子了？
这个the ionization can tell us whether the energy is delivered by one big hit or many small hits.
That's right. I know what you describe as the phenomena. But what causes this phenomena? Okay. You can try to find the answer and let us know later.
Okay.
Also, maybe we go to your conclusion. You have to make a get at least. But the third one, clinical benefit of PPCT is not supported by your data. Could you please clarify this part? 你这个结论怎么得出的？你再澄清一下。
From 3 microscopic models, we can see the proton dose is far exceeds the alpha dose. So we think the alpha dose is undetectable.
Okay. Another is
And
for the BPCT, are there some
is better for meditation,
Mm,
right?
mm.
Maybe you can introduce something about it. 就是PBCT 这实验现在国际上有一些
哦，
验证，可以，也许能解释，对吧？
Now we just compare with the simulations results. Such as the Zooms and GameJ's reports just focus on simulation. So our study just focus on simulation. Thank you. Thank you
for all the questions and all the speakers. And all the packing session. And still come the chair of the back section. I am Dr. Rubin.
And now we finally comes to our closed section. And the first, dear colleagues and friends, this week-long symposium now is about to draw close. On behalf of the committee and academic and organizing committee, I wish to extend my sincere gratitude and congratulations to all of you. And first, let us watch a short highlight video that captures the wonderful moment of this conference. Institute of Modern Physics, and Wang Hailong from ENN Fusion. And the third is Xiao Xiao from ENN Fusion, and Luo Xuyang from Xi'an Jiaotong University, and Yan Xiaotao from Beihang University. Congratulations to all the winners. Please come onto the stage, and the winners please come to the stage, and might invite the representatives of our academic committee and join us on stage to present this post award. Please, Professor Dimitri and Yang Tiesuan and Professor Sun Xiaojun. Winners, please. On here. Yeah. Yeah. These the winners. You present the certificate. Please present our committees. Members, please present. Yeah. Congratulations. Oh. Take picture together. Okay, congratulations again, and you may return to your seat. Thank you. Now there's a very important thing, and it's about next year this symposium. And after very careful deliberation, the academic committee has finalized the value for next year's symposium. It will be held in Xi'an, a renowned and cultural vibrant city. So congratulations to Xi'an. And we have a colleague from Xi'an, and you may say something.
Yeah, thank you. Okay, thank you, Dr. Liu, for the introduction. And I'm Bo Ma from Xi'an University. It's my honor to stay here and represent the Professor Yuntao Zhao and the Xi'an University to express our gratitude to the committee and the ENN for entrusting us to host the next conference in Xi'an. And we recently invite all of you to come to Xi'an next year, and we will do our best to ensure that this important conference is well organized. And we believe that with your support, the hydrogen blue fusion will develop even faster and better. So once again, welcome everyone to Xi'an next year, and thank you all for your support. Okay, thank you very much.
finally, let us welcome the chair of our Summit Committee, Dr. Martin Peng, to deliver the conference closing address.
Well, dear colleagues, and the fourth International Symposium of Proton-Boron Fusion Science and Applications is now drawing to a close. This year's symposium has been larger in scale, richer in academic output, and more international in its participation. More than 40 presentations showcased the latest advances in the field and reflected the wisdom and dedication and hard work of all the participants. Through discussions, you have shared experiences, ideas, approaches, and solutions. I believe this symposium has inspired everyone and provided new insights. The Proton-Boron Fusion Symposium is a bridge to collaboration and shared success, serving the broad proton-boron fusion community. ENN supports the academic committee and its goals. Here, I would like to thank all participants for your support and contribution to this symposium. I would also like to express my sincere appreciation to the symposium organizers and the staff for enduring the greatest hardship I've ever seen for any symposium organization, and using new network capability. As we see, we try to use new network capabilities and ensuring the symposium's success. So let us pull together our wisdom for proton-boron fusion and build an ecosystem of shared success. I look forward to meeting you all and your colleagues in Xi'an. Thank you.
Well, I will formally declare that the fourth International Symposium of Proton-Boron Fusion Science and Application now formally closed. Thank you and see you all in Xi'an, and wish you a nice trip back.
还是到楼下1楼去经商回去，然后那个参观的人是12点半在9层半，12点10分是吗？啊，12点10分在前台那个有个考试课，大家去走。去做交流。
我过去有联系，对，没有，我直接还是我那个会还是
you.